Okay, so here we have an example of a geometric sequence. Now, it seems like there's a pattern to this sequence, and what you can actually do if you divide one term by the previous term, so 6 divided by 2, that gives us 3, and if we do the same for 18, divide that by 6, we also get 3, and 54 divided by 18 also gives us 3. So there is definitely a pattern to this sequence. This number that we found here, 3, is what we call the common ratio of this sequence. And in general, we can describe a geometric sequence as a sequence which has a first term of A and a common ratio, which we call R. So in this example here, our first term A is 2 and our common ratio is 3. Now, this means we can write out a general geometric sequence as our first term being A, our second term is A times the common ratio, R, our third term is the second term, AR times the common ratio again, so we've got AR squared, and our fourth term is going to be AR cubed. In general, our nth term of a geometric sequence is going to be the first term times the common ratio to the power n minus 1. So this gives us the result that the nth term of a geometric sequence is a times r to the power n minus 1. Okay, so you should remember the definition of a series. So a geometric series is the sum of the terms of a geometric sequence. So the sum of the first n terms of a geometric series is going to be the first term plus second term plus the third term. Sorry, third term should be AR squared plus all the other terms all the way up to the nth term, which as we saw is A times R to the power n minus 1. And there's actually a formula for this sum, which we're going to prove. This formula is that the sum of the first n terms is A times 1 minus R to the n over 1 minus R. Now, the proof for this, you need to remember how to do this. So if we write out our series like this, so let's just write this out again with a few more terms in it. So the sum of the first n terms, we're just going to put a few more terms at the end. So we'll put the last 3 terms are in AR to the n minus 3, AR to the n minus 2, and our nth term AR to the n minus 1. Now if we multiply both sides of this by R, this side we're going to have R times Sn. Now we're going to have AR plus AR squared plus AR cubed. So essentially each term we're multiplying it once by R, so we're going to end up with this. So each term is increased by a factor of R. Now if we take away this second line from this first line, so that is Sn minus R times Sn, you can see that these terms are going to cancel each other out, So these terms, there's going to be an AR cubed there that cancels that AR cubed out. And the same, there's going to be an AR to the n minus 3 there that cancels that out, and so on. And what we're going to be left with is actually just A minus, let's write that again, A minus A R to the n. So we can take out a factor here of A. There's a common factor of A in that right hand side. A times 1 minus R to the n. And there's a common factor on this left hand side of the sum of the first n terms, Sn. So that's Sn times 1 minus R. And now if we rearrange this, we get our formula for the sum of the first n terms, just dividing both sides by 1 minus R. And we proved our formula. Now it's important when you're doing this proof that you remember to write out at least the first 3 terms and the last 3 terms of the series, and then the step you need to remember is just multiplying by R. Once you've done that, it should really sort of click into place. And once you've got to this stage here, you know what you need to end up with. So it's quite easy to follow on from that point to get our sum of the first n terms form. Okay, the last thing we need to talk about is called the sum to infinity of geometric series. Now, it should be quite obvious that if we have a common ratio which is greater than 1, then each term of this geometric series is just going to get larger and larger. So a sum to infinity, a sum of infinite terms, wouldn't make sense because that's just going to get really, really large. However, if we've got a value of R that is less than 1 but greater than -1, then each term is actually going to get smaller and smaller. So what actually happens is that this geometric series is going to converge, it's going to get closer and closer to a certain number. Now we're going to talk more about this in class, but there's actually a formula for this sum to infinity. We denote the sum to infinity by an S with a subscript infinity, and that is the first term divided by 1 minus R. And again, this is only valid if R is between -1 and 1. Another way of writing this is the modulus, the absolute value of R, is less than 1.